Okay, so I have some groups for number 10. You guys all went into groups and then you had some discussions. It says provide an argument to prove each conjecture on or provide a counterexample to disprove it. It says all right triangles are similar. Now, some of you are saying yes, and some of you are saying no. I need the no's to explain and I need the yeses to explain. Give me some explanations in the chat, please. All right, so far I got a lot of good words. It says wait, yes because no it doesn't work. What? So they want you to say, is this true or false? All right triangles are similar. So someone said, no, in order for them to be similar, they need to be corresponding and congruent. Very good. So someone else says, all right triangles are not similar because the shapes can be different when dilated. It says, no, because corresponding sides from the two triangles must have equal ratios. Good. Because every triangle is different in size. So all of them being the same would be wrong. Good. I can see that it can be a yes, but for a no, I think it's because the shapes couldn't match up. And then someone says no, the lengths. And then someone says when rotating the points, it wouldn't match up. Yeah. So all of those answers pretty good. And I will just counter example it like this. So I would draw a right triangle that looks like this. And I would say, these are squiggly lines because I can't draw straight lines. So just don't judge. So these are both right triangles, right? And you guys are like, yes. And then so I'd say, but they're not similar. And here's how I can prove that they're similar. Let's pretend this is a 45-degree triangle, and then this is a 60-degree triangle. Like it's a 60 degrees right there. So these are not similar. So I'm going to go like similar, not. Okay, similar is this little squiggly line. And then when I cross things off like that, it means it's not similar. So I just used a counterexample to disprove it. Does that make sense? Very good. Okay. Next one. It says all regular polygons are similar to other regular polygons with the same number of sides. So I'm going to read this one again. So all regular polygons. Do you guys remember what regular means? This is like a definition you might have had in like 4th and 5th grade, so it's been a while for sure. Do you guys remember what regular means? Yes? No. No. Okay. Regular means two things. Number one, equilateral. Number two, equiangular. Okay. So both of those things make up a regular polygon. Okay. So this means all sides are congruent. This means all angles are congruent. Does that make sense? So polygons just means many sides. A quadrilateral, a 4-sided figure, 5-sided figure, 6-sided figure, hexagons, pentagons, like that, are similar to other regular polygons with the same number of sides. So you guys are going to work on that as a group, and you're coming right back to me. Got it? Ready? Go. All right, so if you're watching the video, just pause it and then figure out whether it's true or false, and then come back to me when you're done. Okay, for the second one, number 11, you guys found, most of you came up with the correct answer. It says all regular polygons are similar to other regular polygons with the same number of sides. Now, if they didn't put the same number of sides, business, the answer is no. Because a square will never be similar to a pentagon. Okay, never. Um, I need to be quiet. Okay. So a bunch of you said yes, and your reasonings were really strong. I'm going to copy them into our thing. Someone said, and I really like this explanation, so I'm going to copy this into your notebook. I have to find our notebook. Here it goes. So someone said yes. I'm copying it. Hold on. They said yes. They have the same number of sides. And also, when a translation is done, you can dilate it so that it'd be the same size. Oh, you can barely see this. Sorry. There you go. Is that better? Okay. So can you imagine, like, I don't know, a square and a square, and me zooming that square in to get to the same size? So that's what a dilation is when you zoom in or zoom out. And then make that. So the answer here is yes, because equiangular. So if we're dealing with a pentagon, if it's regular, all pentagons that are regular are going to be similar to all other pentagons because they already have the same angles. And then because the sides are all the same, then they're going to be in that same proportion all the way through, right? Okay, very good. Okay, you're going to do in your groups numbers 12 and 11. You're going to do 12 and 11. What did I say? 12 and 11, 12 and 13. 12 and 13. Okay. So what you're doing here is they're asking you, the polygons on the grid are similar. So you're going to prove whether these polygons are similar by looking and using the grid. You can't use a compass, you can't use a ruler, but just by looking at this here, you're going to determine whether they are. Off the bat, what do you guys think? Yes or no? Off the bat, just by looking at number 12, do you think yes or no? Excuse me. Someone says yes, yes, yes. Okay, good. Off the bat, yes or no for number 13. Off the bat. Off the bat means like your gut guess. You're not measuring anything, you're not doing anything. Okay, so 13, don't match J with G. Match G prime with G. So do you see how it's like rotating all the way around like that? Right? Okay, so I want you guys to try these two. Go to your groups and do 12 and 13, and then we'll meet back here and I'll tell you, you'll explain to me what you said, yes or no. All right, go to your groups. Okay. That's funny. All right, so you guys all came back and I asked your groups, what did you think? Some of your groups said yes to 12, some of your groups said no. All of you agreed that 13 was a yes. So I'm going to go over 13 first because that's just going to confirm your understanding. And maybe by doing that, that's going to help you understand who was right here. Okay. Because for my eyes, I see what it is. I mean, I can tell you what the answer is. So, what I do to confirm that these are similar is the very first thing I can do is I can trace it. Oh, I can't because it's not gonna. I can't rotate it. So, anyway, sorry, I can't do the maximum. I can't like play with our drawing. So, I'm just gonna show you one thing at a time. So, G prime I prime to GI looks like this. Okay, and I have no like Miss Johnson, you said we can't measure on a ruler, but I can measure using the grid. And so the way I'm going to measure on a grid is I'm going to make a kind of like a right triangle. If you want to think about it as a slope, you can too. But this triangle is a 3x4 triangle. Okay. And if I look at this triangle, right? If I continue here and I go up this much, oops, and over that much, I get that this looks like about 1.5 and this is 2. So do you see that proportion there? Like this is doubled. It's doubled that. And everyone's like, oh yeah, I see that. And then you can also see it on the next little segment, which now this is a 2x2. Can you guys all see that this is a 2x2 here? It's up to right 2 or up to left 2. And same thing goes here. This is a 1x1. So we still have that same doubling effect. Or I guess it's halving. It's the halving effect. From here to here, you took half of it. And then the same thing goes here, right? Because this is 2x2 and this is a 1x1. And then this is straight, right? This is 3 and now it's 1.5. Very clear that the sides are proportional, right? And then you'd say, okay, but Miss Johnson, what about the angles? So the way I look at the angles is I'm still looking at slope. And if you remember from, oh no, that was a different class. I'm sorry. If I'm looking at slope of a line, it tells me that they're parallel. So I'm looking at these angles, and this angle here looks congruent to this angle here. Okay, and I can actually prove that, but I'm not going to right now because I just want to get to the next part. So does everybody kind of see how I did this? Okay, very good. This one here, I'm just going to start off with our MN and MN, N prime, N prime. So notice here, every single time we did it, we halved it. We took half of it. We took half of this, right? This was a 2x2, and now it's a 1x1. This was a 2x2, and now it's a 1x1. This was, just 3 units long, and now this is 1.5. So notice our scale factor from here to here is multiplied by 1/2. Does everybody see multiplied by 1/2? There wasn't one section that was not it. Does that make sense? Uh-oh. Yes? No? I don't know. What do you guys think? Yes? No. Okay, I got some nods of the head. Thank you. Okay, so now I notice MN is 2 units long, and N prime is 1 unit long. So it looks like, again, that scale factor is 1/2. Everybody good? So here, if you look at this little triangle here, this is 1, 2. But if you look here, it's the same. From LM to L prime M prime, it's the same. They didn't take half of it. So this is a no. And the crowd goes wild, right? So this is a no because here, this is not times 1/2. I don't care that it's times 1. I really don't. I just know that because we went half here, then that means everybody has to experience half. And that's not true. Yeah, I know, right? I know some people are like, yes, I won. The other reason why I said no was because, like, if you look, like, this and this almost look like a square to me. Like, this side was congruent to this side. Maybe, I mean, I can prove actually that these two sides are congruent, but this didn't look so squarey. Like, you see how this looks like part of a square? But this isn't, it's not, that triangle. It doesn't look like part of a square. So that's how I knew. So for those of you who got it wrong, I'm so glad that you got it wrong during class, right? Instead of getting it wrong during the test. So very, very good. Any questions on this? What was the hard part? What part tricked you? You tell me what part tricked you. And while you tell me what part, I'm going to just read the next one. It says, a sequence of transformations occurred to create the 2 similar polygons. Provide a specific set of steps that can go from one image to the pre-image with 1, 2, or 3 transformations. Yeah. So those are the ones who got tricked. I will say It's because you didn't check all sides, right? You kind of were like, oh yeah, it looks like it. Let me just check one. Oh yeah, it works, right? But notice here, I checked every single side. Because remember, the definition of similarity is all sides are all corresponding sides are proportional. So all, that means you need to check all of them, right? And that's part of your diligence, right? Here, it looked like it. I mean, it looked really good. But then as your eyes, like train your eyes to be very like picky, right? Like this, if I like covered this part, doesn't this part look like a square? Doesn't this part not look like a square? Right? Yeah, this part to me looks like half of a square. All right, let's move on. So you're going to write a series of transformations in order to get this guy to get to that guy. Oh, someone still is not convinced. So I'm going to convince you one more way. And I can use drawings on this one. So I will. Excuse me. So I'm going to trace this guy here. I'll try to do a good job of it. Oh, that's a bad job of it. Sorry. I said I'm going to do a good job of it. And then I messed up. Okay. Let me just go like this. Okay, that's pretty good. That's a pretty good trace, right? So what I'll do is I will... Ooh, can I do this? Oh, yeah, I can. I remember. Sorry, I was trying to figure it. So, okay, so I'm going to grab this guy by using this tool. And then so now I'm going to bring him over here. I'm going to line him up and see how I can't get him quite right. And then I'll make him smaller so that MN matches MN. See how that doesn't match up anymore? Like it's all not working. And some of you are like, but Miss Johnson, you're not very good at tracing. I'm like, I know, but it's not even close, right? Because even if it's just a little bit close, but do you see how like all these extra little sides are hanging off the edges there? So that tells me, no, this is not going to work. Okay. All right, back to over here. So what you're going to do is you're going to write me a series of steps. I'm going to rotate something. I'm going to translate. I'm going to slide it. I'm going to reflect it. Your job is to get this on top of here. Now, in real life, if I just handed you two pieces of paper, you stack them on top of each other, you kind of like tap them against the desk so that the corners will all line up and then you're done. Here, you got to give me directions. Okay. So you are going to work on, actually here, I'm going to let you guys choose between these four. Yeah. Between these four, your group gets to choose. Kind of choose one that like you're like, okay, I think this one is fairly approachable by myself. So choose that like the quote unquote easy one, and then choose the one that looks a little bit harder. Okay. Okay. Words that I'm looking for: rotate, reflect, center of dilation, dilate. Right. Those are the words I'm looking for. Yes. Okay, so I'm going to open up the rooms again, and you guys are going to come back as soon as you're done. I'm thinking about 6 minutes, because then class is over. Go, quickly. Okay, so for number 14, right, how do you get this over here? Now, it kind of looks like a rotation, and I was kind of trying to trick you by drawing an arrow like this. And some of you already said in the chat, that's awesome. It is a reflection. Very, very good. This is a reflection. Now, the way that I know that it's not a rotation is if I start rotating C, like imagine me rotating, like pulling this image, right? And I'm pulling him until he gets on top of C prime, right? Or C, is that C double prime? Geez, C double prime right there. The B would be sticking out up here. So you could say that you rotated it and then you reflected it. That's fine. But the bigger answer, the more correct answer, I think that's a better way to say it. The more correct way, not more correct way. No, there's just many different ways. So I'll just say it like this. The way that most students are going to see this is that they're going to reflect this across this kind of like, can you imagine I fold this line like this and I get that C matches up with C double prime and that B matches up with B double prime? Does that look like a good fold? That actually looks like a pretty good fold. Okay. And so, so when I reflect it across this line, I'm done. But there's many different ways. Like you could have, that's one way that you could reflect it across this line. Another way was you, just the way we said it, we could rotate the figure and use A as the center of rotation. Does everybody see how it's going around? But then we have B sticking up here, and then I would reflect it down. So there's a couple different ways that you could do this. Okay, I wanted to really quickly before time runs out, but time already ran out, is show you these ones. This is the most important part of our lesson, okay? And this is kind of where I want to make sure that you guys hit. So if you haven't done these 3 problems, and actually it's one problem, it's number 19. It says determine whether or not these pairs of triangles are similar and explain why. So again, your only options for triangle similarity are going to be AA similarity, or I guess we should say AA triangle similarity, sorry. SAS triangle similarity and SSS triangle similarity. Okay. So those are your options. Some of you are already like, oh, I see some of them. You're right. You do. So then as soon as you see, let's say like one of them you think is AA similarity, you're just going to go AA similarity. That's it. These two are similar. Why? Because of AA similarity. These two are similar. Why? Because of AA similarity, or whatever the case might be. I will just tell you, these two are similar because of AA similarity. Do you guys all see this angle matching up with this one? This one matching up with this one? That's why they're similar. Okay, so I need you to figure out B and C. These are the most important ones. You will see one of these on the quiz and the test, okay? All right, really good job today.